It's really a great pleasure to have Xinliang on from National University of Singapore, who made a very, very long trip to tell us today about low regularity ill-posedness for elastic and ideal compressible.
Okay, I would like to thank Leo for the invitation. It's such a great pleasure to see all these friends and also to be back to Fields Institute. So I perhaps the second longest, so the longest probably is Todd. I think he probably even further than me in Australia. Yeah, okay, so yeah, okay, so we'll talk about the ill-posedness for elastic wave and for ideal compressible MHD, right? So in this talk, we will discuss some physical system with multiple wave speed. So the first system we look at would be the elastic wave system. So the equation of motion is the displacement of an isotropic homogeneous hyperelastic material from a quadrilinear hyperbolic system, which is of the following form. So U is a vector, which is U1, U2, U3 being scalar unknowns. So there are constant C1 and C2, which is larger than 0. So if you take the divergence part and the curl part of one, you will see two wave equations. One is with wave speed C1, one is with wave speed C2. So the right-hand side would be the nonlinear term. So there are many terms, and they are all of the form like gradient U times second derivative of U. So more precisely, there is some very precise structure, which is at least over here. So Q is being the standard noun form. Okay, so this is the first physical system we want to study. And then the second physical system, which is the ideal compressible MHD. So this is composed of Euler equation and the coupled Maxwell equation. So this is also form a quadrilinear hyperbolic system. So the first two lines are actually the compressible Euler equation, but with the magnetic field coupled in it. And the third equation is for H, the magnetic field, and S is entropy, and this is the second equation. So, right, so this would be the two main system that we will study for this talk, right? Okay, so for this talk, the goal is we try to understand what would be the sharp regularity threshold for both local well-posedness and for the low regularity ill-posedness. So my talk will be more addressed for the ill-posedness part for this talk, but we will see the threshold, right? Okay, so the consideration of this, actually, we can starting from consider a single quadrilinear wave equation. So this is the equation 3. So for this equation, its Cauchy problem is local well-posed in HS cross HS minus 1. So which is as long as S is larger than 2, there is the local well-posedness. So first proved by Smith-Tataru, and then proved with a more geometric method by Qian Wang in 2017, right? So for this equation, if we take an additional derivative, the form of 3 will be transferred into a form of 5. So the equation of 5 actually is more similar to the quadrilinear, the elastic wave system, which we just mentioned. And then the local well-posedness threshold H2 will be shifted to H3. So in our talk, we will use both forms 3 and 5 actually in later slides. So I list both of them here, right? Okay, and for the ill-posedness part, so in 1998, so Lindblad gave the sharp counterexamples to local existence for certain typical model equations in R3. So 6 is the equation. Okay. Yeah, this is the equation. This is the equation he's considering. So note that this equation actually is well designed. So which is of very particular form. So D is like partial x1 minus partial t. This is because by this equation, the solution there are some a little bit more precise formula for the solution, and you can do things very explicitly. And so for this equation, quadrilinear wave equation, he showed that there is the H3 ill-posedness, and in particular, when there is ill-posedness, so the H2 norm of the solution actually blow up instantaneously, right? Okay, so 20 years later, so Ross Granowski, so he studied, he tried to extend the ill-posedness, the result of Lindblad, shows that for equation 6, the ill-posedness mechanism actually is stable on the non-plane symmetric perturbation. Okay, so right, and also he showed that the actually ill-posedness is driven by a shock formation. Okay, so in Limba's talk, it's already secretly hidden that the ill-posedness is also driven by a shock formation, but you need to go through the details to say that. Yeah. Okay, and this is for 3D, and for 2D case in 2021. So a student of Krieger Ullman actually generalized Limba's 3D real ill-posedness result for the same equation 6 for the 2D case. He proved also the corresponding ill-posedness result in a fractional Sobolev space-time. We'll see this very soon. Yeah. Okay. So okay, and then how about the other part, which is the low regularity local ill-posedness part? So yeah, so we consider several parallel linear hyperbolic system. Right. The first is Einstein's equation. So we consider Einstein vacuum equation in R3+1. So because of the proof of bounded L2 theorem, so we know that for this Einstein vacuum equation, the local ill-posedness is for HS for S larger or equal to 2. So historically, so there are quite a few proofs towards that. The first proof actually was, okay, one of the proof actually was done by Kleneman and Rodiansky. And they first used wave coordinate to show that if S is larger than 2, there is a local ill-posedness. And the sharp case, okay, the sharper one was by Kleneman, Rodiansky, Sheftel. It's so-called bounded L2 theorem, and they use Yang-Mills frame show that if S is being 2, there's also the local ill-posedness. And so if we consider using wave coordinate, so Ettinger, Limbaland actually show that so H2 actually is a threshold because in wave coordinate there is ill-posedness in H2 in wave coordinate, but in Yang-Mills frame we know that there is the local ill-posedness. Okay, so the other system is for the Euler equations in R3+1, and also we have the low regularity local ill-posedness. So we know that this Euler equation, compressible Euler equation, actually is local ill-posed in HS cross HS prime, with both S and S prime larger than 2 with respect to velocity and vorticity. So this was proved by Visconti, Luo, Mazong, Speck, and also Qian Wang, and also later by Huali Zhang and Anderson. And so they proved this for the compressible Euler equation, and Sifan Yu is here. So he extended this for the relativistic Euler equation and proved the desired low regularity local ill-posedness result. Okay, and then so okay, yeah. So in particular, if we consider the vorticity, there is an interesting kind of connection to the incompressible fluid, which is we don't see this connection really explicit, but it's a weak connection, which is for in the community of incompressible fluid. So respect to the vorticity, there is the H3 actually ill-posedness. So yeah, first proved by Bogenli and later revisited and give another proof by Kim and Zhong. Right. Okay. And the third system, which is for the admissible harmonic elastic wave system. So harmonic elastic wave actually material is a kind of well used material in material science. And within this family, there is a kind of a special family called the admissible harmonic material, which enjoys slightly better decoupling structure. And for that structure, together with Haoyang Chen and Sifan Yu, we show that this system have the H3 plus and H4 plus local ill-posedness with respect to divergence part and the curl part. So for both the result for Euler equation, like the low regularity result we mentioned here, and also for this result, those results we will see would be sharp in terms of the velocity and the divergence part. Okay, so we will see the ill-posedness very soon. Right. Okay, so right now back to our talk. So the first result about the ill-posedness is we show that the Cauchy problem for the 3D elastic wave system actually are ill-posed in H3 cross H2 in the following sense. So so we construct, sorry, we okay, yeah. So in the following sense, so we construct a family of compact supported initial data with the parameter eta. Okay, so as eta goes to 0, the size of the initial data in H3 norm actually goes to 0. So for each eta, there exists a finite shock formation time t eta star, and so before eta star, the solution remains smooth, and at t eta star there is a shock. And in particular, we can see that at the t eta star, the H2 norm actually blow up, right? Okay, so this is the sense of the ill-posedness. Okay, so right, this is a good question. So you mean eta go to 0?
When eta goes to 0,
right. This is a very good question. So there is a little bit subtlety here, right? So it depends on how you set up the data, right? Okay. So there are two versions. One is the stronger version. One is the slightly loose version, which is I chose the loose version. The slightly stronger version is if you assume some additional assumption, you can show that as eta go to 0, the theta star go to 0 to give you instantaneously shock formation, right? Yeah. Okay. Right. So. Right. So.
What sort of assumptions do you need on the data?
Right. That's a good question. Right. So which is because in order to show that the theta star go to 0, so even though the proof will say mainly based on plane symmetry, but because you want to have the finite energy, so there is a region which is not the plane symmetry. You have a region here. So assume that you can. We have a way to demonstrate that. So there is small argument over there. So if you do not worry about that, so this is the safe one. If you work actual things over there, you can get a better result. Yeah, but there's some argument you need to go there. Yeah. Okay. Right. So, right. Okay. So, right. So let's see. Right. Okay. And for the MHD system, so we also have that it will be ill-posed in H2. So, yeah, in the following sense, which is we still have the a family of data given a parameter eta, as eta go to 0, so the H2 norm go to 0, and we have the shock formation time theta star, and similarly theta star is the shock formation time, and for this one, so we have the H1 norm actually blow up at the theta star, right? Okay, and also back to Jerry's also Leo's remark. So for theta star go to 0, so if you consider H2 minus, this is very easy to say. So if you consider data which is in H2 minus, you will see that at eta go to 0, theta star go to 0. So really sharp case is for H2. So this is requires some argument. Yeah. Right. Okay. So right. Okay. So in particular, if we let H2 be 0, so our system reduced back to the 3D compressible Euler equation, which is considered the following 3D compressible Euler equation, allowing non-trivial entropy and the vorticity. This is the equation actually here. So our result implies the below H2 ill-posedness result for the Cauchy problem. Okay, it is like the follows, which is so yeah, the same, which is so we know that the Cauchy problem of 3D compressible Euler equation is H2 ill-posed with respect to the fluid velocity and the density. So there is a family of compressible initial data with parameter eta. As eta go to 0, the data go to 0, and we have the shock formation time, and the H1 norm actually blow up, right? Okay, so this is a picture for the compressible fluid because the local well-posedness part actually is better established, right? So let's first say that there are the vertical line corresponding to the regularity of vorticity, the HS S prime, okay, and the horizontal line corresponding to the HS, which is S regularity for the velocity, right? So the classic local well-posedness gives the gray triangle, which is this region. So which is in this region, we know there is a local well-posedness, right? And so our ill-posedness corresponding to this solid line, corresponding to which is velocity actually being L2, and vorticity could be smooth here, right? And in this very thin region, this is really the hard effort made by discounted law, Mazen Speck, and later Qian Wang. They show that also Zhang and Anderson. They show that they have a local well-posedness in this region. So this blue square region is still open at this moment, but people believe that there should be a local well-posedness, but still not proved yet. So this corresponding to this one corresponding to the vorticity being H3/2. So intuitively speaking, so this may related to the ill-posedness for the incompressible case, which is for Bourgain's result. So they have this solid line. For the incompressible case, it would be ill-posed, but this region is still open at this moment. Yeah. Okay. So right. Okay. So the remarks for our approach. Right. So yeah. So which is so similarly to Limlad's work. So we initially work starting from plane symmetry, but we want to see the more physical system with, in particular, with multiple wave speed. So, yeah, so we denote the x value. Okay, so we denote x to denote x1. Okay, and assume that the vector actually unknown function u1, u2, u3 depend on only on x1 and t. But this is a plane wave solution to elastic wave equation. So keeping the quadratic nonlinear term, actually, so this satisfies the following equation. So for this equation, you can see that for elastic wave, there is top order coupling. Top order coupling means for the first equation, this is the wave equation for u1, but on the right-hand side, you will see the second derivative of u2, the second derivative of u3. Similarly, for the second and the third equation, you will see the second derivative of u1 here. So really coupled at the top order, right? Okay, so yeah, as one will see, so later we will treat this as a 6x6 first order hyperbolic system with top order coupling, right? Okay, and for the MHD system, so it is 7x7 actually first order hyperbolic system, which is of the following form. Yeah, we will see this later. So to show the ill-posedness for it, so we will combine a geometric approach and an algebraic approach. Okay, so let's first state several results about the shock formation. Right. Okay. So yeah. So because we want to show that this ill-posedness is driven by shock formation, we really need to understand well about how this shock forms. So yeah. Okay. So there is a geometric approach which is used to study for quadrilinear wave equation and to show that the shock formation actually can form geometrically. So the first, okay, so yeah, there are old results using natural motor, but let's say, so usually when we consider geometric method, so starting from Cristolo in 2007, so yeah, he showed that the shock formation for 3D compressible relativistic Euler equation under the irrotational and anisotropic conditions, and he introduced the inverse foliation density mu, and as mu go to 0, you can see that there's a shock formation, and he found the formulas and the top order energy estimate and so on and so forth. Decent scheme to show the shock formation. Okay, and then later, so the non-relativistic version actually was proved by Cristolo and Miao in 2014. So and then Speck, Haozaigo, Luke, and Wang show that the stable shock formation, which is near simple plane waves. Okay, and then Miao and Yu, they consider a scalar quadrilinear wave equation with cubic nonlinear terms, and consider large data is kind of like a short pulse prepared data, and they also can show that for this one there is a shock formation. And then the work by Luke and Speck, they include the vorticity into the dynamics, and they find the very nice structures and show that the shock formation for compressible Euler equation with vorticity, and so there is a wave transport system. Okay, but still there's one wave operator, and okay, almost the same year. So Speck, Jerry, okay, so he showed that the shock could form for wave system with two different wave operators. So this system is slightly better than elastic wave or MHD. So there's no top order coupling, but the low order actually are coupled together. And also there is a very recent, very important work by Abrasel and Speck. They show that the emergence of singular boundary for 3D compressible Euler equation. This is a geometric approach, right? And yeah, recently there is also a different approach where self-similar variables. So which is prove the shock formation for compressible Euler equation with vorticity. So for this approach, the data is more well prepared, right? So okay, so which is close to a progress profile and so on and so forth. So right, so this approach is by first by Buckmaster, Scholar, and Waco, and they prove shock formation for 2D and 3D, and results by their group later, right? Okay, so yeah, so recently with Haoyang Chen and Fulin Qi and Wenzhe Su, so we use this method to do something actually, yeah, which is we found maybe interesting, right? The first is we extend this kind of setting to the curved background, and we show the shock formation can really happen on the sphere S2. Yeah, because so this approach So because the data is actually, initial data is more restrictive, so the framework compared with the geometric approach, like in the previous slides, so here, this is really heavy, actually, calculation and heavy proof. So, but for, let's say, the approach, like what we did here for our work here, so we can prepare the initial data such that we can have the argument in a slightly okay, the more easy way to show the shock formation and adapt to the curved background. Okay, so for example, one of the work actually is currently we are working on. We want to show that our ill-posedness, which is just stated for the on the plane symmetry, mainly on the plane symmetry for compressible Euler equation, this would be a stable phenomena. So which is we want to show that yeah, without we want to remove the plane symmetry assumption, and because we can prepare the initial data quite precisely as the linear type of initial data. So this actually approach is quite precise to capture the answers. So yeah, so we are working on that. I think this is actually hope that this could be obtained in the okay, the paper could be okay, get ready in the near future, right? Okay, yeah.
Do you need positive curvature, or could you have done?
Oh, that's a good question. So because for S2, so the shock formation actually is still a local in time result. So does not really rely that. But in the right, but it really in the cosmology setting, this is a very interesting question related to this actually result. So if you are in a expanding universe, also generates result, and you may not have the shock, right? So so actually the physical reason for this is we want to study, for example, the compressible Euler equation on Earth. So this is why, for example, the cyclone along the equator usually be studied using compressible Euler equation on that. So this is why we choose this model to consider. So right, okay, right, okay. So yeah, okay. So back to our ill-posedness, right? So we reformulate the Yasovic system or the MHD system by 6x6 matrix or 7x7 matrix. Okay, so for the after we write down this in a metric form, so we can calculate what would be the eigenvalue for the matrix. And the first interesting thing is we find that both systems actually are not strict hyperbolic. So it means, so there are 6 eigenvalues, but lambda 5 and lambda 4, the other pair is lambda 3 and lambda 2, they could be very close with each other. So in particular, if your phi is 0, lambda 2 and lambda 3 are the same, lambda 4 and lambda 5 the same. And also in the end, we want to show there is H2 norm inflation, right? Okay, so this would be the eigenvalue lambda 1 to lambda 6, and A, B, C, D actually are parameters. As we can see that, if you let C and D, which is in particular the sigma 1 to be 0, and if you plug in there, you will see lambda 2 and lambda 3 they are the same, lambda 4 and lambda 5 they are the same. So it's really that it could be possible that the elastic wave is a non-hyperbolic, non-strict hyperbolic system, right? Okay. So the thing actually we need to do is, so we need to calculate the left eigenvector and find the corresponding right eigenvector satisfied this algebraic inner product delta ij condition. And from here, you can already see the left eigenvector and the right eigenvector are not unique. So this is really the key for some of our calculations. So this gives you a room to do renormalization, because some of the calculations or the structure is only good for one of the choice, and the other choice will give you singular terms. Okay, so I will mention this maybe later, right? So yeah, so if you choose the proper right eigenvector, okay. I also want to mention that this is also the difference of our result compared with a previous result. So in previous result, usually when they consider the left eigenvector and right eigenvector, they usually impose another condition, which is the the inner product of size 1 to make it normal. But you will see that for this system, you cannot do so, because you will have something to be infinity. And so you would have to allow that one of these norm to be infinity, one norm to be 0. But okay, I mean, okay, at a certain point, right? But okay, but there exists such a, we do need this kind of condition, make this Li and Ij to be unit, but this is actually can be achieved, yeah. Okay, right. So this would be the left eigenvector and right eigenvector. So for MHD system, there is also additional lambda 4 in between. So they have a 7x7 system. So okay, and in terms of the result, so we need to explore more subtle structures about MHD to get the ill-posedness result. Okay, right. So yeah, so we also have this non-strictly hyperbolicity. So the lambda 1 to lambda 7, which is of the following form. So CF, CA, and CS are the fast, the often the slow wave speed. So yeah, this system is also non-strict hyperbolic. So when H2 and H3 are both zeros, so we will see that the lambda 2 and the lambda 3 are the same, lambda 5 and the lambda 6 are the same. So this is the place we need to really be very careful about how to choose the left eigenvector. So, so we carefully design the right eigenvector and the left eigenvector. Okay, and so there is only, I mean, we have the freedom to choose so, and as long as you times any function actually still the left, okay, corresponding function inverse, right? There are infinite choices, but there is a particular good one, which if you choose the correct one, so you can yeah, guarantee that the splitted structure actually, the equation of the structure with of good terms, because if you consider the coefficient in front of nonlinear terms, you will see many coefficients. In particular, there is a dangerous term, which is 1 over, the dangerous term is like a coefficient, like 1 over H2 square plus H3 square. As we know that H2 and H3 could be very close to 0. And if you didn't choose the left eigenvector and right eigenvector correctly, so this would be the really singular coefficient, and we cannot do things. But there is a particular one of the choice, and after we choose this, all these terms will be cancelled either by the numerator being the add up of H2 square plus H3 square, all those terms will be cancelled, right? So there is, by choosing this special left eigenvector, so we verified almost 300 terms and the dangerous terms, and they all cancelled, right? Okay, right. Okay, so the decomposition of wave. So this is the method actually we use. So which is we define the inverse density of the ice characteristic. So because we have several waves traveling in this region. And so when rho I goes to 0, it means there is a shock formation within the ice strip. This is corresponding to yeah, the vanishing of rho I characterizes the shock formation within the ice strip. Okay, and we also define the Wi and Vi, and yeah, this is partial phi, which is of the following form. So the wave decomposition method was first invented by John in 1974, and sharpened later by Cristolo Paris in 2015. So, but both works actually are studied strictly hyperbolic system. So our work actually generalized this method to the non-strict hyperbolic scenario, and also to the ill-posedness result. Yeah. Okay. So, so we will use two types of coordinate. The first one, which is the more traditional, the characteristic coordinate, which is for the initial data starting from Zi, you run an characteristic and ODE, and you have a T, so with the Zi and the T. Okay, and for lots of cases, we need to do something more actually precise and more subtle. So we need to use the so-called bicharacteristic coordinates. So which is, for example, this point, if you along the Ci family, you go back to the point Yi, and if you along the Cj family, go back to the point Cj, then this point with the coordinate Yi and Yj. Okay, but there is only one catch, which is if you change between these two coordinates, if you go to the bicharacteristic coordinate, so by changing to this characteristic, usually involving a factor which is 1 over lambda I minus lambda J. Okay, so this is the reason why before our work, so the bicharacteristics are usually work for the strict hyperbolic system, which is when lambda I and lambda J are not equal with each other, right? But for the cases we are facing here, lambda I and lambda J could be very close with each other. We need to overcome this difficulty. We will see this the next page how we overcome it. Okay, and this is the structure of the equation. So this is really the key of the things. So which is after this wave decomposition. So for example, for Wi, we will see a list of Riccardi type equation. And the structure here is very important. The first one is for example, the first one is the partial S1 W1, which is W1 squared. So which this term actually drives the follow up, which is later. And there's no W2 and W3 term and no W4 and W5 term. Because lambda 2, lambda 3 could be very close, lambda 5 and lambda 4 would be very close, so which means there's a strong interaction between W2, W3, W4, and W5. But for the first equation, we don't have. And for the second equation, which is for the derivative of W2, so there are the potential quite dangerous term, which is W2, W3, and W4 times W5. But the lucky thing, which is the good thing from the equation, from the structure, from the equation, is there is a small coefficient in front of it, which is lambda 2 minus lambda 3 and lambda 4 minus lambda 5. So this is really the important the thing we find for this elastic system. The reason why this actually is very useful is because of this structure. So now we can use bicrystal coordinate of this one. So because in order to get more precise estimate, which is we need to use that one. But for that term, it will involving 1 over lambda 2 minus lambda 3. Okay, but luckily that dangerous term will be cancelled by the coefficient, right? So which means if you so there are also 4 okay, there may be several others, but all these places can be handled in such a way, which is this is why we can generalize John and Christolos method to the non-strict hyperbolic system. This is for the elastic wave system. So there's also the other family of wave. They're also structured here. Also for the rho i's, also some structure, right? So physically speaking, this is the picture. So we designed the complex support initial data from here, and let it with the initial data, let it run. So there would be 6 waves. So waves travel along R1, R6, and as we already see, the lambda 2 and lambda 3 would be very close. Lambda 4 and lambda 5 would be very close. So in our analysis, we consider this as a union kind of strip. There are also the gray region in between. The solutions are not 0 here, but these are different regions. We all need to use different norm to capture the different estimates, right? Different interaction and different estimates, right? So we will show that rho 1, which is really, rho 1 has an upper bound and a positive lower bound outside of R1, which is for the first strip, okay, which is if you travel with the speed lambda 1, there's no shock from here. So it only, the rho 1 actually will tend to 0 within R1, so which is the first shock actually happened in R1. All other rho i's in the whole region, they are bounded from both below and above, so there's no shock, and it's really the W1 actually blow up along here. Okay, so so MHD system, there is also structures. So but the structure is a little bit more subtle than elastic wave. We need to do more work about the estimate. This can also be done, right? Okay, so so which is so I already explained that this is the region we want to, for all these different regions, the estimates actually are all different, but this would be the region actually we will consider. For MHD, there's the additional R4, which is in the middle. Okay, so what would be, this is the first shock. For both pictures, the shock actually happened for the fast wave, which is happened here, right? So before T8 start, everything would be smooth, but this would be your first shock. Okay, so in summary, so for T8 less or equal to T eta star, so as long as your I is not 1, so for example, rho 2 to rho 7, okay, or rho 2 to rho 6, they are all bounded away from 0. So there's no shock within that family of curves. So, and rho 1 actually obeys a positive lower bound outside of R1, and within R1, actually it goes to 0. Okay, so and we just know that the first shock actually happened within the R1. Okay, and we also can prove that all these VI, they are all uniform bounded in the whole region. And in particular, it will be used for later argument, the rho 1, so V1 has a positive lower bound. Okay, and similarly for WI, so as long as your I is not equal to 1, WI actually is uniform bounded in this region. So W1 actually, which is the quantity which will blow up, so obeys a uniform upper bound outside of R1, it only blow up within the R1 together with the shock formation time, right? But so so this is, if we do the estimate, control the thing, this is what we can get. But how get this related to the ill-posedness? This is the follows, right? So which is for rho 1, we have very precise estimate, which is so we have this is coming from the initial data, and we can see that all the coefficients we can calculate quite precisely. So that's the shock formation time actually with both upper bound and the lower bound, which is in such a way. So as we can see, this depends on eta. So it depends on the choice of the initial data we set up. So if we want to let this go to 0, we need to choose the suitable ones of W0 and eta, right? Okay, so yeah, this is the case we will see the ill-posedness. So so we considered L2 norm of W1, okay, and so we by estimate there is a lower bound which is of the following quantity. So the shock at the shock formation space-time point, which is 0 0, and with the time t eta star, so we know that ρ1 is equal to 0. This is precisely the place we use the shock formation, which is we minus 0, which is minus ρ1, which is the quantity here, and then we use intermediate value theorem. So this is bounded from below by this quantity. And moreover, in our estimate, so we can show that the partial Z01, there is a uniform upper bound, okay? And thus there is also a lower bound, which is this quantity. And we know this goes to infinity. So thus we know that why the L2 norm of W1, actually it blow up at T eta star. And we really use the shock formation information for here. So this L2 norm of W1 actually translated back to the physical language. This will give you the second derivative of the displacement actually to be infinity for elastic wave, and the first derivative of the velocity, or the first derivative of the density actually to blow up. So this is how we see the norm inflation here, right? Okay, so those actually are for 3Ds, and for 2Ds we will see that for the 2D it's so the nonlinear structure would be slightly different, which is of the following form, which is Q12 is also another non-form. Right. So yeah, we have the MHD system. We have also the for the 2D scenario. If we let H1, H2 to be 0, we also go to the 2D compressible Euler equations. Okay. The different and also the interesting is so for 3D, so the threshold would be H3 and H2, but for 2D, the sharp threshold would be the H11/4 and H7/4. So which is when you design the answers of the proof, or when you design the initial data, you need to be more careful about this this regularity, or there's a way to achieve so. So we have similarly the ill-posedness result and for the 2D scenario, and yeah, and also for compressible MHD. And if you reduce to the 2D compressible Euler equation, we will also have the H7/2 ill-posedness and like consistent with other result before, right? So if this is still the pictures, right? So this what we call it the HS prime, S prime for regularity of vorticity. This is for HS, which is regularity of velocity. So for this triangle region, this is the classic local ill-posedness result. So our ill-posedness actually is along here. So if we consider the incompressible analog, so this corresponding to the ill-posedness by Bourgogne and also later by Jiang, which is they indicate there may be ill-posedness result here, right? And so this single region actually was claimed by Huali Zhang, and this region is still not known, right? And if we consider the density and the vorticity, this is also similar. So this is our counterexample of local ill-posedness, and this is the classical result. And this region actually is not known. This actually is claimed by Zhang, right? Okay, so so for the I still have time. Okay, right. Okay, it's good. Yeah. Okay, so yeah, so this is actually I move to the second topic, right? The second topic is if we consider the multi-wave speed system other than Euler, Einstein, there is also the Einstein-Euler, like in Maher's talk, right? So which means the ultimate goal is we want to say something about, we want to understand something about Einstein-Euler, right? Okay, so let's first say that for Einstein vacuum equation, what do we know about the gravitational collapse, right? Right. So with my student Tao Ranhe, so he's now a postdoc at IHES. So we wrote a preprint last year, and which is on Kerr black hole formation with complete apparent horizon and a new approach towards Parent's inequality. So with new hyperbolic arguments and the new elliptic framework, so we prove the follows, which is we consider a scenario in the gravitational collapse, which is which is there's a region which would be Minkowski, and there's short pulse data, which is shooting toward the inner region. And after the short pulse, you turn off the radiation. So there would be some small decaying data here. This would be a characteristic initial value problem. We want to know what would be the final state and what's happening, right? So we show that, right? So with scale critical short pulse initial data, like what we just see that the Einstein vacuum equations admit the slowly rotating curved black hole formation solutions. Okay, so this is the Penrose diagram of the solution, right? So which is initially, so in the short pulse region, there would be the formation of a trap surface and the formation of the apparent horizon. And the apparent horizon is emerging from a point. This is like a cone, and it grows. And there would be a transition region. It will slowly settle down. And then in the later stage, the curve stability will kick in, and finally it settles down to a curved black hole, right? And so in this process, so we, so there are a lot of things actually we need to do for this argument. But let's say, just see that other than the hyperbolic part, so we can have a very precise understanding about the apparent horizon, which is we can show that the apparent horizon, which is the boundary of the black hole region, emerging from a space-time point and being space-like in the beginning, as the area become larger and larger, and being a chronal, which is for the whole dynamics, and asymptotically none, and then eventually converging to the event horizon, and with and its curve value, and at time go to infinity. So it's really settled down to a curved black hole, right? So so based on this picture, there is some interesting geometric quantity actually we can study. So for example, so there is related so-called Penrose inequality, so which is want to relate the area of the modes with the ADMS here, right? Okay, so let's see what we found. So by this argument, actually, we found that along the apparent horizon, the area of the modes actually is never decreased. So it increased in the beginning and then never decreased toward the future. So which this is why the square root of the area divided by 16 pi actually will become larger and larger, and eventually there is a limit. The limit is related to the m infinity and a infinity, the final mass and the final angular momentum of the curved black hole. So this is so-called the irreducible mass, actually, and we can calculate the limit that goes to here. And by algebraic calculation, so we know that this quantity will be less or equal to m infinity. Okay, and along the future non-infinity, we have the bounding mass loss formula, which is the bounding mass actually will become smaller along that direction. So if we along this direction, which is the bounding mass will become larger and larger. So in particular, if you go to the ADM mass here, so this will give the inequality, which is precisely this one. So so this actually in this black hole formation, in curved black hole formation space-time, this gives the desired Penrose inequality, which is without time symmetric assumption. So because we know that for the time symmetric scenario, the geometric analysis side of mathematical GR community, so they use inverse mean curvature flow or conformal flow to prove from some Penrose inequality with time symmetric assumption, right? But but time symmetric assumption for them actually is something they want to overcome, but a little bit hard to overcome. But this is a scenario which is a physical scenario, which is we do not use parabolic method, we use hyperbolic and elliptic method. So we show that if we consider in the region of the perturbative curve regime, or let's say in this curved black hole formation regime, so we really have this desired Penrose inequality. Okay, so what is the thing? The thing is the follows, right? The thing is the left picture, this would be the original trap surface formation result for Einstein vacuum equation by Cristolo in 2008, and by using a lot of previous results, so including my work with Luke for this region, and nonlinear curve stability, lots of results here. And so we can show this is a hyperbolic spacetime, and we then do the final analysis of things here. We show this would be the general picture for the gravitational cloud without any symmetry assumption. So together with Sifan Yu, so so we are able to extend Cristolo's first result to the Einstein Euler system. So in particular, we can show that the trap surface can form in this similar setting due to the focusing of fluids, while the initial data for the shear tensor being small. So this is a little bit different from the Einstein vacuum perspective. So for Einstein vacuum perspective, with the shear tensor is quite large. You could consider the fluid to be a perturbative thing, right? So which is the shear tensor still dominates and you can get a travel surface formation. But here we want to do something different. We want to do something more physical, which is we hope that the fluid actually would be dominant, at least for the initial data, and the shear tensor to be perturbative, right? And so this would be the result. I hope that with the Sifan we can have the paper ready within this year. And I think we end talk here. Thank you. Yeah.